Okay, so this lesson is about patterns in math, and what I want to talk about is a couple of things that you need to know. You need to know a sequence is an ordered list of numbers. Each number in the list is called a term of that sequence. And when you deal with those sequences, you have really two types. You have an infinite sequence, which just goes on forever, and that's pretty simple. And then the three dots are called the points of ellipses at the end of the sequence, indicate that the same pattern continues for an infinite number of terms. So, like if you have something like 2, 4, 6, 8, dot, 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 and then you got like 1, -3, 5, -7, 9, -11, 13, dot, dot, dot. And if you got something like 2, 1, 2/3, 2/4, 2/6. Yes, I know that's 1/3. 2/7, dot, dot, dot. So can you finish the next three terms of the sequence? Well, obviously, 2, 4, 6, 8, that'd be 10, 12, 14. And I guess this one would be what? 15, 17, 19. And then I guess this one would be 2 out of 8, 2 out of 9, 2 out of 10, right? So that's pretty simple. Talk about sequence notation. Sequence notation, the following notation denotes specific terms of a sequence. U sub 1 just means the first term. U sub 2, guess what that means? That's right, the second term. So the nth term is determined by U sub n. The term before the nth term is U sub n minus 1, and before that one is U sub n minus 2. So if we want to do the ninth term, would be u sub 9, and the u sub n minus 1 would be 8. Okay? So you can kind of see how this works. So this is the first term, this is the second, third, fourth, fifth, dot, dot, dot. And then this would be like all the way to the end of un, and then the one before it, and then the one before that. So you may not have a lot of experience with that, but it's just some basic terminology that you need to know. Let's continue drawing the pattern shown below by drawing the next two diagrams. Well, I kind of did it for you. So you see, you got two circles, and then two, two, and then one more, and then two, 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 and then boom, boom. So then this one goes one row of two, another row of two, another row of two, another row of three, and then dot, 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 and then this adds another, and then another, right? So if we had to come up with something, I guess this is the first term, so that's two, and then there's two, four, there's five there, and then I guess that's eight. How many is that? Two, that's 11, and then 14, and then dot, dot, dot. So if I wanted to say u sub 1 is 2, u sub 2 is 5, u sub 3 is 8, and then we just say, okay, well then what is u sub n? Well, how is this pattern happening? Well, it looks like what's happening is we take the previous one and we add 3 to it. All right, that's pretty simple, right? Um, when you're looking at a sequence, when you're looking at, whoop, that's not right. When you're looking at a sequence, it says graph the first 5 terms of the sequence. So realistically, you could say this is the first term, second term, third term, fourth term, fifth term. So you could graph like 1 comma 2. I'm sorry, yeah, 2 comma 5, 3 comma 8, 4 comma 11, 5 comma 14. Now if I graph these things, doing that real quick, and there's 1 and then 1, 2, put a dot right there, and then 2 and 3, 4, 5, put a dot right there. Oh, I'm sorry, right there. And then 3, 6, 7, 8, put a dot right there, and then 4, and then 1, 2, 3, and it's 11, and then 5, and then 1, 2, 3. Looks like a line, right? Well, that should make sense because if you graph the sequence term, comma, the number in the sequence, and it makes a line, it's what's called an arithmetic sequence. Because there's another type which is called geometric, but this is arithmetic Arithmetic sequence. Arithmetic sequences is when you graph it, it makes a line. Look at this guy. Um, this one you can well this one if you graph the sequence, it makes a like a curve, like an exponential growth. This is what we call a geometric sequence. Okay. But if you look at this, it goes 1/4, 1/2, 1, 2, 4. What's happening is it's doubling the previous term. That's what this is right here. This right that means it's a recursive sequence, a recursive function or recursive sequence, and it's pretty simple to do. It takes a little bit of practice, but we'll probably deal with that here in class or something. So let's talk a little bit about some sequence. So a basketball is dropped from a height of 8 feet, hits the floor, bounces to a height of 6 feet, continues to bounce, and on each rebound it rises 3/4 of the height of the previous bounce. What would be the next term of the sequence? And then write a recursive formula for the sequence that represents the height of the ball on each bounce. Make a table and graph showing the height of each bounce, and to the nearest tenth of a foot, what would be the height be on the fifth bounce? So there's a few things that we can do here to make it a little bit easier. First off, what do I know? I know that it starts with a height of 8 feet. And then it hits the floor, it bounces to 6 feet, and it continues. So the next term, so I guess if I just would do 6 times 3/4, right? 6 times 3/4, I believe that's 4.5, right? I believe that's 4.5. Now, if they want us to write a recursive formula for the sequence that represents the height of the ball, well, I guess I could say the next term, u sub n, is pretty much u sub n so I guess that would be un minus 1, the previous term, times 3/4. But you could polish this up and make it 3/4 times u n minus sub n minus 1, which is the previous term. All right. If we wanted to do a table for each bounce, I guess you could just do it by hand, right? You can just do a table by hand. It wouldn't be a very big deal. Um, so I guess if you think about it, we go 0 bounce was 8. 6 was first bounce was 6, I think, right? Second bounce we just figured out was 4.5 feet. Third bounce, I don't know what's 3/4 of that. That's 3.375. 4 bounces would be 2.5313. Fifth bounce, I guess 1.8984. And then sixth bounce, I guess, would be 1.4238. You just keep taking the previous by 3/4. So looking at the table, I guess you would say on the fifth bounce, the ball bounces 1.9 feet in the air, I guess, huh? Let's look at another application. So Rick owns an automobile dealership. Last year, he spent $16,000 in advertising. He plans to increase his advertising expenditures by $1,200 this year and in each subsequent year. What will be the amount he spends in advertising in the sixth year? Find a recursive function to represent this problem and use a table and a graph to find the solution. Well, if you're smart about it, you probably know, okay, well, if you start with 16,000 and he's adding that, it's going to be un is the previous term plus 1,200. So if you make a table, we got to find out how many years is it? Sixth year. So So first year 1600, second year 17200, third 18400, fourth year add 1200 was at 196, fifth year 20,800, sixth year 22,000. So there you go, 22,000 bucks. All right. Mrs. Long creates an endowment fund for her alma mater. She places 250,000 in the fund to start, and she'll add $50,000 to the fund each year. She states that 25% of the total amount in the states that 25% of the total amount in the fund shall be used for scholarships. How much will be in there in the fund at the end of the 6th year? All right, so there's a few things here. First off, she's going to use 25% for that. So really, the previous term or the next term is 75% of what? What's it say? She will add 50,000 to the fund each year. So it's the previous year times 75% plus 50,000, right? And then you can do a table. First year she started with was 225,000. Second year, plug it in there. I guess that's 202,000. No, 206,000. 250. Third year, 192,188. Fourth year, 181641. Fifth year, 173730. Sixth year, 167798. There you go, right there. That's that. So hopefully that makes sense. And sorry that this is so long, but you can handle it. May the force be with you.